Hi, we are Engineering Brothers, and once again we have come out with our another interesting problem over here. And according to our title, you can see that this is our consideration for our torque voltage analogy additional problem one over here. As we all know that we have already covered up our previous problems regarding our torque voltage analogies over there. Right now, we are just going to take or choose some complex problem over here. That is why we have considered our three angular displacement sections over there, and the three angular displacements are theta 1t, theta 1t, and of course quite naturally theta 3t. And we need to find out what are the connected elements with our theta 1t, theta 2t, and theta 3t over there. And J1, J2, J3 are quite naturally our moment of inertia, and this is analogous with our force voltage analogies over there, and force voltage analogies or that concepts are applied for our translational system. In this consideration, we are just trying to consider on our mechanical rotational systems over there. So if you do apply the torque over there, or on that consideration we have applied the force. In this current consideration we have applied the torque over here, and after if you do apply the torque over here, and because of that applied torque the angular displacement is happened over there, or happened or that is transferred throughout our setup or towards our mechanical rotational system, and because of that applied torque we have got theta 1t, theta 2t, and theta 3t over there. So the steps are the similar accordingly, and we no longer do require to repeat the same procedure over there. I just try to solve our given problems over here. If you have missed our previous problems regarding our torque voltage analogy, please do follow our previous videos. On that videos we have totally given you what is the exact process or what is the exact important or crucial steps to solve the torque voltage analogies over there. Right now we are just going to follow up our given steps over there, but before I go into much needed steps over here, I'm just once again try to refresh your mind in order to solve or in order to show you the important steps over here. The first step will be quite naturally our we need to convert this conventional mechanical rotational system into our nodal diagram over there. So we need to convert our given or this given diagram into our nodal form of diagram. Okay, so we need to first construct our nodal form of diagram. That is our first step. And in our next step, just by applying our D'Alembert principle on our because of our displacement of our angular displacement of our theta 1 theta 2 3 theta 3 3, we have got three different equations over there. So our next step will be we are going to apply the D'Alembert principle. D'Alembert principle. I have already given you what is the exact meaning or what is the exact process to apply the D'Alembert principle over there. So first we are going to form or construct the nodal diagram. We need to convert this conventional diagram into a nodal form of diagram, and in our next step we do require to apply the D'Alembert principle on our displacement angular displacement theta 1t, theta 2 3, theta 3 3 over there, and after that we have got our much needed differential equation. So we have got differential equation. Just by applying the D'Alembert principle we have got our differential equation. And what is going to be the number of differential equation? As we have got our three different angular displacements over there, because of that we have got our number of three differential equations over there. So the first step will be we do require to convert this given mechanical rotational system into our much needed nodal diagram over there. And in our next step, just by applying the D'Alembert principle on our theta 1 3, theta 2 3, theta 3 3, we have got our three differential equations over there. So this is our third step. And in our fourth step, as this is our torque voltage analogies over here, we are going to utilize this chart over here, and we do require to convert this our much needed mechanical differential equation into our electrical one over there. And how do I do that? Just by matching these analogous quantities over there. And what are the analogous quantities? The left hand side of our parameter, or this left hand side portion, is indicated that these are our mechanical parameters over here. So at the first one, we can say the torque, and the torque is analogous with our voltage E, and that is been applied for our torque voltage analogy. So one will be matched with our one. So the torque is analogous with our voltage. In our next part, we do have the moment of inertia. So the moment of inertia is analogous with our inductance, and we do know that inductance is quite naturally our electrical parameters or electrical passive elements over there. And in our third part, we have got the damping coefficient, which is B, that is analogous with our resistance over here, the another quantity for our electrical one over here. And in our next part, we do have the stiffness, which is K, that is analogous with our 1 by C. 1 by C means our 1 by capacitance. And in our fifth part, or in our fifth points for our analogous table over here, we have got the angular displacement, which is been indicated or referred as our theta 3, that is analogous with our charge, which is qt. And at the last stage, we have got the angular velocity omega t, which is analogous with our current I. So we do require to match these mechanical parameters with our electrical one over here. So this one will be our mechanical equations over there, and we do require to convert that mechanical equation into our electrical differential equation just by using this given analogous table over here. So what is the meaning of our analogous consideration over there? I have already mentioned in our previous classes that the equivalent quantities over there. So the torque is equivalent with our voltage. So though we do know that, or we have realized that these are our two different systems over here, the right hand side of our system do indicate the electrical one, and the left hand side for our part is being considered as a mechanical part. So we do require to make the bridge in between these two different systems over there. The left hand side is being considered as a mechanical one, and the right hand side is being referred or considered as our electrical one. So we do require to construct two different systems over there, and that bridge should be constructed over here, and that is the exact definition, or that is the exact thing for our torque voltage analogy. So the torque is being referred to as our mechanical rotational systems over there, and the voltage is quite naturally referred to our electrical one. So we do require to match these two different systems over there, and that is the exact meaning of this torque voltage analogies over here. So this differential equation is quite naturally or mechanical in nature. And in our next step, just by utilizing this analogous table over here, we do require to convert, or just by replacing this parameter, or just converting this mechanical parameter into an electrical one, we have got our another set of differential equation, and that once again the number of differential equation is 3. But what is the exact difference for our in between a 3 and 4? This differential equation is electrical in nature. Okay, this differential equation is quite naturally the electrical in nature. Now at the last stage, we are going to form the circuit diagram just by looking at this electrical equations or electrical differential equations over there. So at the last stage, we do require to form the electrical circuit. and that will be the final stage for our torque voltage analogy problems over there. So I am just going to repeat our same procedure over there. First, we do require to convert this conventional mechanical diagram or conventional mechanical rotational system into our nodal form of diagram over there, and in our next stage we do require to apply the D'Alembert principle on our each and every one nodal each and every one angular displacements of theta 1 t, theta 2 t, theta 3 t over there. And after I have applied that one, we have got three differential equations over there, and I do require to mention over here that mechanical equation or that differential equation is quite naturally the mechanical one. And in the next stage we do require to convert that mechanical equation into our electrical one just by using or just by considering this chart or analogous table over here. So we do require to convert that mechanical system into electrical or mechanical equations into electrical ones over there. That will be our fourth stage. So at the fourth stage we have got the electrical differential equations over here, and at the last stage just by looking at that electrical differential equations we do require to form the final circuit diagram or the final electrical circuit diagram, or more specifically the electrical circuit diagrams over here. So that will be the final destination point, and that is the exact solution for our torque voltage analogy problem over there. So these are our important steps that we are trying to follow while solving this given problem over there. But I have already completed, or I have already given you the much needed steps in our previous videos over there. If you have missed that previous videos, please do follow our previous videos. So I have just followed, or I have just given you those important steps over here, and from our next consideration or for our next part of our video, we do require to follow these crucial steps over here. Just stay tuned to the classes to follow our videos. Just wait for my next part.
If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.